So what's going to happen today, so besides the class here, is if you're interested, I will put up a mock quiz on Blackboard for this material that hasn't been on a quiz yet, which is what we're going to do in a second. And I'll put up the answer sometime tomorrow. As with the other mock quiz, if you want, you can send it to me and I will grade it. Obviously, you don't have to, and it does grade. So if you don't do it, it's not a big deal. Monday is our last class, and so what I'll do is, as I said, do maybe a little bit more in chapter 1, talk about what's going to be on the final and how it's going to work. Also next week, at either Monday or more likely Tuesday, because I'm grading stuff through the weekend and Monday, I will put up a mock final, which will somewhat look like what you'll see in actual final in 2 weeks. And the reason I want to do that, even though you have probably 5 or 6 old finals on Blackboard, is this semester is, as you might suspect, a bit different. So a decent number of the problems will be multiple choice. So I want to put up one that has those types of questions so you can see what it's going to look like. It won't necessarily have all the material that could be covered. For that, you'll want to look at a couple of other old finals also. Okay. All right, so so it isn't up yet, so I'll put it up later today. It'll be on Blackboard. It depends. So some of the multiple choice ones, there will be questions where if you make a little error, you'll get that. In that case, you could get partial credit. But other ones which aren't worth as much will probably be just right or wrong. So the one thing is the multiple choice won't be worth as much because, yeah, you can't get partial credit. But there will be some that do have partial credit. All right, so let's start with an example from 4748 with the plate one. There really aren't many good ones in the text, so let me just make up one. So this is a 4748 question. So a plate, remember for this, we're assuming it has a unit thickness. So when we set up the area, we're basically setting up the volume. And then we use the idea that mass is volume times density. So here's our picture. Fairly straightforward one. And try to fit it all on one page, which is mass, and then the x and y coordinates of the center of mass. So we have it all together. So how do I get the mass? It's the integral of what? Oh, that's actually first little thing, which is what are these 2 points? So the point on the left is when x is equal to right, so this is which which you would get by setting the x squared equal to 8 minus x squared, which would give 2x squared is equal to 4, so x squared is equal, 2x squared is equal to 8, so x squared is equal to 4, and x equals plus or minus 2. And then back to another question, so if the thickness wasn't unit thickness, so in general, mass is something that would be in calc 3, because what you would do in that case is pretty much what we did with the wires, which is to get the mass, you would integrate the density function over the using the triple integral. So it simplifies a little bit in some ways in calc 3 because you just integrate the density function. Right. And so this is, in general, we do the density and then times the sort of volume, which is in this case the area, which in this case is the top curve minus the bottom curve. So the 2x is the density, the 8 minus x squared is the height, dx is the width, so that gives us an area, and since we're assuming it has unit thickness, it means it's a volume. So the 2x is the density, everything beyond it becomes the volume. And if, like here, I'm just asking you to set things up, then you should label it so then you can use it in the next part, next two parts. And so I can fit things again, let me shorten things. So now let's find the x coordinate of the center of mass. And so it's going to look partially similar to what we had in part A. What do you add to get the center of mass to the integral that we have in part A? Right, so 1 over m in the front. Obviously, you can simplify in writing it. So x times this. And remember, what we're doing is we're getting the average of all the values of x from -2 to 2. So we're multiplying the value x, and everything else, this part divided by m, is the weight of that point. So we're getting the weighted average of all the x's. And then C is, let's find the y coordinate of the center of mass. But before I set up the integral, which I will, is this one we don't really need an integral to get the center of mass for the y coordinate. It's not completely obvious for my picture. It's, as usual, my picture isn't drawn very well. But what is the center of mass? And in some ways, the 2 gets the idea, but is slightly off because we're looking for the y. So what is the center of mass for y? 4, right? So at 2, so at x equals 2 or -2. So you can see if I had drawn this well, my picture is symmetric around y equals 4. And since the density doesn't depend on y, it is just the center. But let's do it anyway. And as I've said for the last few classes, we want to put a y there, but instead, what do we put here in place of the y? And once you put it in, you'll see that, oh yeah, it does become 4. So instead of the y, we do the 2 functions divided by 2. So add up the 2. So the 8 minus x squared plus x squared divided by 2. And then everything else is the same. I said, this last one, you can see, oh yeah, this really does just give 4 because obviously the x squareds cancel. So we get 4 in the parentheses, which is a constant. I can pull it out. And I can then see that the rest of the integral is what the integral in part A. So we get 4 over m, the integral of our integral in part A, which is m, and it simplifies to 4. So this is the 3.7, 3.8 problem that wasn't on the last quiz or test. So any questions on this? Okay, so let me look at 3.9. In this one, there are a couple examples, so let me do a couple of the homework examples. So from 3.9. As I said, for this one, there are also examples with kinetic energy and stuff like that. You can ignore any of those. I forget if there's still some in the homework or not. So 25, it's a bucket of sand. So a bucket one. Thank you. And this needs to be a constant because otherwise it gets a little weird. So we have a bucket of sand that's being lifted at a constant rate of 4 feet per second. The bucket contains 80 pounds of sand and is leaking at a rate of 0.5 pounds per second. In some ways, I'm writing what they did. Think of it not as 80, the bucket contains 80 pounds of sand, but the bucket with the sand is 80 pounds and is leaking at a rate of 0.5 pounds per second. How much work to lift it 60 feet? So we know from the basic one that if we have force as a function of position, then work is just the integral of the force. So we did the one example with the spring. The first few examples in the homework are just giving you the force as a function of position, and so therefore those you're just going to do the integral of the force as given. Here it's just a two-step thing because we have the force in terms of time, but we need it in terms of position. So we have that the velocity is equal to 4. So that gives us that the position at time t is 4t. And we're also given that the bucket, which since it's in pounds is a force, is the 80 minus the 0.5 t. So we did one of these before, so you can see this is just almost the basic one where force is a function of position. It's just that you're going to have to do the little substitution because we have force as a position as a function of time, and we have position as a function of time also. So if I solve for t in the first equation, I get t is equal to x over 4. And this is the base one, similar to the spring one we did, and as I said, similar to the ones at the beginning. And at that point, it's just because remember, for this one, the idea is we know work is equal to force times distance. And what we're doing here is we're breaking up that 60 feet into lots of tiny little pieces. On the tiny little piece, we can assume the force is constant, and we multiply the force by that little distance. Then we let that little distance go to 0 and look at the sum. And in the limit, the little distance becomes the dx, and so the force times the distance gives us the work. And you get some number. As with the pyramid ones that we did before, all the tank ones, here, since we're given pounds, we don't have to worry about gravity. If we're given this in kilograms, we'd have to multiply by g to make it into a force. So here's kind of the base one, which is the base one is of one type is work is equal to force times distance, which gives us that work is equal to the integral of the force if force isn't in a constant. So here's the one type. Any questions on this? Okay. And then the other type is the one we've done a few examples of, so I'll do one more of those, which is sort of 42. Here, instead of writing all the other dimensions, let me just put them in. So the cone has a height of 30 feet, bottom radius at the base of 8 feet, and water up to a height of feet. And we want to find the work to empty from the top. So this is what the problem does, but let me add in something like this, just to make it so that we've done more complicated ones, so that if on the final you do get one of the basic ones, hopefully that will be simpler than what we're doing now. So in the problem, it says just do it to the top of the work to get it to the top of the tank. Here I'm going to say to a platform that is 5 feet above the top of the cone. So we do kind of our usual thing. We say, well, what we want to do is a generic slice, and since it's a cone, the cross-sectional area is a circle. The cross-section is a circle. And also, as usual, there are two distances we're going to care about. This distance, which is the height of the similar triangle that we're building. And this distance, which is how far I'm going to move that generic slice because I'm going to move it from there to the top of the platform. So we have the two things we care about, and we're going to call one of them X. The last couple, I did both, but here let's do one, and then you'll tell me how it changes if I switch. So any preference between which one is X? Do you want X to be the inside one or the outside one? My two brackets. Any preference? This one. Okay. So X, so the 30 is the height of the cone, so from the base to the tip. So let's let that be X. And so we need the other one, which is this. So what is, if that is X, what is this? In some ways, if you look at it, it's fairly straightforward. It's the X plus the 5. And that's supposed to be a plus 5. So we do the same thing we did in the last view, which is we have to get R in terms of X. So here, what is R in terms of X? R divided by X. That's equal to, yep, 8 divided by the 30. And we know that area, of course, is pi r squared. So we get the area is pi r squared. And therefore, our force is that multiplied by the density. Do I need to put in G here? No, because this is pounds, which is a force already, which is why even though you sort of know that gravity in feet is 32 feet per second squared, you will never be using it for these problems. And then work is equal to this. And then I have to multiply by the distance, which is, as we said from the beginning, is the X plus the 5. And what are the limits? And so again, we're remembering we're moving the pipe down from the top. So therefore, in terms of X, when it first hits the water is when? So what are the limits? So as it is, it's 20 to 30 because we're measuring down from the top. So as I move down, the first time it hits water is 20 feet from the top of the cone, and that's what we're calling X. So the other possibility is we switch the X and the X plus 5. And if we do that, pretty much wherever you see an X, you're going to make it an X plus 5, and you're going to make the X plus 5 into X. So these two things would switch. And in the new one, what would be the limits for X in that case? So if X is the distance from the top of the platform to my generic line, then what are the limits in that case? So if I switch again, I'm measuring down from the top, and now the first place I hit water is 25, because I'm measuring from the platform, which adds 5 feet to the distance. Again, if you put it in at 20, this is 20 and this is 25. At 25, you will get 25 and 20. So we'll get the same thing. Yes. No. So in some ways, when you're doing this, you should just get used to doing it one way. So for example, you can always let x be the height of the similar triangle, and you can always do it that way. So yes, obviously, you only have to do it one way. The only reason it might come up that you should be able to do both ways is if it is part of a multiple choice, then you don't get to choose what is x. It would be chosen for you. So you'd have to know that if it was this form, that also works. In some ways, you'd have to be able to see how it shows up, because you'd have here the 4 however many possibilities, which one of those comes from letting one of those two things be x. And as I said, that's in some ways why I want to do the mock final for you next week, so that you can see how that might work. So any questions on this? So let me see. So I was also asked about 39, but I think that is, which I'll talk about with this one in a second. It's a simpler version. Right, so, oh yeah, so 39 is, we have a rectangular length, in which case, the reason it's the simpler version is that it's rectangular, so the cross-sectional area is a constant. So it's going to be something similar to this, except you don't have to worry about similar triangles. So when we get our cross-sectional area, it's just going to be a constant. And you'll multiply by the density. And in that case, it really won't matter what you let x be, so you might as well let x be the distance from the top. Because when we talk about this, which compare this to the last one, which in the last one, we integrated the force, and the dx was the distance we moved it. Here, we don't really want to do that. What we're doing instead is we're cutting up the cone into lots of little slices. On the little slices, it's basically a little cylinder, and therefore we can pretty easily get the volume of the thing. And so in this case, this dx here is the thickness of the little cylinder. So this times this is the volume of the little square I've made by making the little cuts. And then this is the distance I'm moving it. So I'm breaking up in a different way. So in some ways, we have these two ways of breaking up the integral. So any questions on this? All right, so this is the last thing that could be on the final. But since many or most of you will go into Calc 3, let's at least quickly do some of the stuff in Calc 3, Chapter 1. Usually it's actually on the final, but this is, again, not a usual semester. So So 1.3 we got to quickly yesterday, and we got to the definition. Which is this. And remember, the idea of it was that theta is the angle between them. So in essence, what we're doing is we're multiplying the lengths of the two vectors if they were in the same direction. So the length of u times cosine of theta is the length of the part of u that's in the same direction as v, which we used for work, because work would be then the dot product of the force and the vector, how far I've moved. And we also ended with that if we're actually doing a dot product given two vectors, it ends up being easier than that. Sorry. All you do is multiply the corresponding components. So the 2 times the -4 plus the 1 times the 2 plus the 5 times the 3. And you get back a number answer. In this case, since I don't tell you what u and v are, it doesn't mean anything, but we get a number answer. If u was the force and v was the displacement of the movement, then this would be the work. So in some ways, we don't use the definition for doing the basic part of the dot product, because we have this simpler way of doing things. But we can kind of go backwards and use it to find, here are two angles. What's two vectors? What is the angle between them? So if we put the two tips together, we can ask about the angle between them. And we can use that using the definition. So this also lets me do, and I should have done better numbers. Reminder from previous section, what is the length of the vector? And it's the same as the distance of a point, which is just the square root of the sum of the squares, basically the Pythagorean theorem. Same thing for v, the -4 squared plus 2 squared plus 5 squared. So 16, so 20, so square root of 45. And if I bring the definition down, I get then the cosine of the angle between them is the dot product, which we just got. This is not a negative, that's just a stray mark. And then I can use the calculator to get that angle by using the inverse cosine. In some ways, it doesn't matter which units we use, but since we're in calculus, what units should we really get the angle in? So here I put theta is equal to 1.2, what are the units of that? So in general, it could be radians or degrees. In this case, in calculus, remember, we like radians better because calculus deals with lengths and radians is a length, whereas theta is not. And also going back, if you remember, in theory at least, the derivative of sine of theta is cosine of theta if we're in radians. If we're not, officially it's the cosine of theta times, I always forget, pi over 180 or 180 over pi, whichever way it goes. So it's not, in this type of setting, it's not a big deal if you use degrees, but really should be in radians. Okay. So here is kind of base thing. So definition of dot product, how we do it, and then how we can use it to get the between two vectors. So let me kind of continue, which we sort of did. Which is, this is the picture I started with, which is I have, except I called it force and the displacement vector. Here I'm calling it u and b. And what we did was we multiplied the length of v times the length of u times cosine of theta, which is our dot product. But as part of that, I also want to be able to get this vector. Which is what is the projection of u onto v. As I said, this is kind of the typical physics thing, which is we have the vector u, and I want to break it up into a piece of the vector that's parallel to v and a piece that's perpendicular. So that's PROJ, project, right? And since I didn't write it very well, there it is there. So let's look at the picture to figure out what it is. So the first part we've already used, which is I know the length of that thing. Because we use that in getting the definition of the dot product, just the length of u times cosine of theta. That's the length of the vector I want. And the direction I want is, well, the direction of v. I want it to be in the same direction as v. And since that's all we need to get a vector, we're done, right? Because we need the length and we need a direction. The little thing is, and you'll have to remind me because I didn't write it from before. Actually, I think I remember. Is remember that the direction of a vector is the unit vector in the same direction. Which is just the 1 over the length of the thing times the vector. By dividing by the length, we make the vector have length 1, which is a unit vector. Therefore, if I put those two together, now the way I get the vector is multiply the length times the direction. And I get that as the projection. But what I'm going to do, and I lost the length I'm going to multiply the numerator and denominator by the length of v, because then I can use my simpler way of getting dot product. So just multiply the numerator and denominator by b. And that numerator now is the dot product, so we get this formula. That's all a number, and then times the vector. So let me start. I was going to continue the last one, but let me actually do another one, because then we can do all the parts together as a second example. Also this way, the numbers will be nicer. So here are two vectors, and to make it simpler, I'll make it two-dimensional, but all the things work whether it's 2 or 3 or however many dimensions. So here, what is the dot product of these two numbers, these two vectors? So again, it is component by component. So yeah, so you get the 16. So now let's get this new thing. Let's find the projection onto V of U. By the formula from the last, it is this dot product divided by the length of what we're projecting onto, and then times the vector V. So we just need this, the length of V. What's the length of V? In some way, since we're going to square it, we can actually get rid of the square root, but it's the usual square root of the 12 squared plus negative 5 squared, which is, I think, 13. It's 144, 25, yeah, so 169. And so therefore this is equal to 16 over the 13 squared. That's a number times the vector. And if you're asked for it, if I was asking for it, I would either allow you to leave it like this, or you can multiply by the number, so you get whatever that is, 16 times 12 over 13 squared, comma, 16 times negative 5 over 13 squared. And so this is the vector that is now parallel to V, and it's the projection. Little question. So let me pretend this is V, this is U, and this is the projection. Well, we just got that little vector at the bottom of the triangle. But as I said, in physics, usually what we do is we want to break up the angle in the vector into two pieces, a piece that's parallel and a piece that's perpendicular. So the question is, how do I get this vector? Often we don't care about that, because if, for example, if we're doing work, we don't care about this vector because it's perpendicular to our direction of movement, and so it doesn't matter. So we could use sine, or I can use the fact that what is this vector plus this vector? So if I add those two vectors, the projection plus this thing I want to find, what am I going to get? Yeah, so in some ways I'm checking to see if you remember how to add vectors, which is you put them tip to tail and then draw from tip to the tail of the second one. So what I can do is just subtract. So any questions on this? So in some ways this concept generalizes. You can project onto a two-dimensional surface on a three-dimensional surface and so on, which you might see in physics, but we don't see in Calc 2, Calc 3. So any questions on this? This is 1.3. So I'll only do one more thing. So that's dot product. And let me skip 1.4, which is what I might add in on Monday. And since there aren't too many of you here, let me just ask. How many of you, have any of you seen cross product of vectors? Anyone else? Right, so places it's coming, yeah, so I assume a lot of you, if you've had physics, it comes up, because in some ways this isn't really a definition. Although I'm labeling it that way. Is going to get the cross product of two vectors is going to give us a vector that's perpendicular to the two we started with. A little thing, in this context, we sometimes start using the word orthogonal instead. Orthogonal is kind of a more general term than perpendicular. And two, and has the area of the parallelogram formed by those two vectors. So if I have the two vectors u and v, if I put them like that, if I make it into a parallelogram, then the area of that thing is going to be the length of the vector I get. So that obviously isn't really a definition. It's just what we want. So these are more properties than the definition. To get how you do it, so the first thing is the cross product really only makes sense in 3 dimensions. So 1.3, the dot product pretty much makes sense at any number of dimensions you want. Cross product really only makes sense in 3 dimensions. And the reason we care about this here, and more importantly into Calc 3, is once we get into 3 dimensions, we're no longer going to have tangent lines, as the tangent at a point will have tangent planes. And the way you get the equation of a plane is we need a vector that's perpendicular to the plane. So the cross product will be a way of getting a vector that's perpendicular to planes. So it'll start coming up a fair amount in Calc 3, as it probably has in physics. And in the background, we'll see if I can do this in 5 minutes, because obviously it's not on the test. Final is we need determinants. What is the word indefinite? Is perpendicular. Perpendicular, yes. So the cross product of u and v is perpendicular to u and v, has the area of the parallelogram formed by u and v, and that picture is the parallelogram. So we need determinants, and that is kind of a two-stage definition. So the determinant of A, which is written with vertical lines like that, of a 2 by 2, we can define. So since you've seen cross product, you've probably seen this. What is the determinant of this matrix? And a matrix is just any array of numbers that's rectangular. So what's the determinant of this thing? In some ways, determinant is really just a tool. Kind of the original use of determinants was solving systems of linear equations. That became less useful, but it still comes up in lots of places. So I do a 2 by 2. And this we definitely do quickly, because it's really just a way of remembering what the cross product is. So the determinant of this matrix is that. As I said, by itself it doesn't really mean anything, but it's a tool to getting. So for example, if this was a system of equations, 2x plus 3y equals something, 5x minus 4y equals something, and we went to solve, this would be a tool to get that solution. I really use x0, 1, stuff like that. But so for 3 by 3, the way it works depends on the 2 by 2s. And if you've done this, there are different ways of doing it, but let me do the kind of the most straightforward one, which is using the first row. So using the first row. And then the determinant of this is that first number times the 2 by 2 matrix I get if I ignore the row and the column that A is in. So I ignore the first row and the first column. And whatever's left. And then they alternate. So positive A minus the B. And now ignore the row and the column that the B is in. So ignore the first row and the second column. And then again, they alternate, so plus C. Ignore the first row and the third column. And now these are all 2 by 2s, which we know how to do from the previous one. And at the end, you would get back a number. And again, the number by itself doesn't really mean much, but it would be a tool for example, solving the, in this case, 3 equations with 3 unknowns. So as I said, the matrices and the determinants isn't really what we care about. So here is now and let me actually just do an example since we only have the 5 minutes. So if I have u is equal to u, way we get, or a way we get the cross product is we make this first row, oh, sorry. So yes, it alternates. So an alternate sign. We make the first row I, J, K, which I'll remind you what those are in a second, but if you've done the physics, you know what they are. Put in one of the vectors as the second row and the other vector as the third row. And in the background, these are shorthand for I is shorthand vector 1, 0, 0, but you want to leave it as I. So it's the x coordinate, J is the y coordinate, and K is the z coordinate. And now we use what we had above, which is it is I times the matrix I get if I ignore the first row in the first column. And again, they alternate, so minus J. Ignore the first row and the second column. And then plus K. Ignore the first row and third column. And now they're 2 by 2. So you can see I don't have much room here. This is -2 minus 6. So I get a negative 8I. This is -4 minus 2. So -6, but then multiply by the negative, so plus 6J. And then this is a 3. So 6 minus 1, so that's 5. So plus 5K, or in the more usual way, it's after -8, 6, 5. And this we can pretty easily check to see if I've done something silly, because this is supposed to be perpendicular to these. And I didn't really talk about it, but since the dot product gives us the cosine of the angle between, or uses the angle between them, the only way perpendicular is if the angle between them is 90 degrees, and cosine of 90 degrees is 0. So if u and v are perpendicular, their dot product should be 0. And if you look, the dot product of u and this new vector is -16 plus 6 plus 10, which is 0. So it is perpendicular. And if I take the dot product of v in this new vector, I get -8 plus 18 minus 10, which is the 0. So those two vectors are also perpendicular. So the cross product gives me a vector, which I'm going to want for the plane, a vector that is perpendicular to the two vectors I started with. And if I now took the length of this, the square root of the 64 plus 36 plus 25, that would be the area of the parallelogram that these two vectors form. So really quick intro. That way, in Calc 3, they'll do the same thing. They'll actually spend a bit more, even though they're in its review, they'll spend a bit more time going over this again. And Monday, I'll probably just, the first 10 minutes, just remind you or tell you what the equation of lines and planes are, and maybe do one example of each. Because that way we'll do tangent, when you get into Calc 3, where you're doing tangent lines in more than 2 dimensions, and when you're getting tangent planes, you'll at least have have seen it once, so it is at least partial review. So any questions on this? Obviously, I'm not assuming you know it real well yet. Okay, so otherwise what's going to happen is later this afternoon I will put up the mock quiz on Blackboard. And then tomorrow at some point I will put up the answers to the mock quiz. And as I said, if you want to treat it like a quiz, see if you know the material, you can take it and send me an email of your answers, and I'll grade it as if it's an actual quiz. And then next week, Monday, we'll do the quick 10-15 minute intro to the lines, and I'll talk about what's going to happen with the final. And either Monday or, as I said, more likely Tuesday, there will be a mock final that I'll put on Blackboard. so you can see what the actual final might look like, since this semester is different. Yeah, so well, today's the usual day, Monday's the usual day, Tuesday I think is, but what I usually do is, so I have finals, our final is on Friday the 24th, so the last possible time. I also have a final on Wednesday. So what I usually just tell people is all the other days, that would be next week from uh, Wednesday through Friday, and then the following week, Monday, Tuesday, and Thursday, I'll just have Zoom open in some form from 1 to 5, and I'll put the link up on Blackboard. And if I time out, because if no one has come in for a while, it times out, I think at like half an hour, 40 minutes, just send me an email and I'll just go back in. Yeah, so in some ways for the final, that's what I'm talking about. Then next week, probably on Tuesday, I'll put up a mock final on Blackboard, and that will look like you will see in the actual final. So I'll make it so it's about the same length. It won't have all the possible material, so it won't really be a review. It'll be something similar to what you'll actually see. Oh, yeah, so it'll be similar to what you did on the test. Like, I'll hopefully not make a mistake, which is you'll download the thing and upload the answers. We for the instructors have been talking, and we're kind of assuming that it's sort of open notes. But what I tell people is, on the other hand, we make it so it should take an hour and a half or something, and you have 2.5 hours to finish it. So if you haven't at least organized your notes well, the notes aren't going to help you because it'll take too long for you to go through your notes. So you should treat it like it's closed book and maybe just write up a page or two of notes, because otherwise you won't be able to use them. It'll take too long for you to find everything. Okay, any other questions? Okay, so let me stop recording. I'll stick around for a couple minutes.